In 1980, a hole opened up in the Texas desert near the town of Wink. Not a small hole, not a pothole or a crack. A sinkhole 110 meters wide and 34 meters deep, appearing overnight, swallowing the surface above a location where an oil well had been drilled in the 1920s and improperly abandoned decades later. They called it Wink Sink 1. In 2002, another hole appeared 900 meters away, larger, 200 meters across. Wink Sink. Researchers from the University of Texas Bureau of Economic Geology and the U.S. Geological Survey began watching both sites carefully. And in 2019, using satellite radar data capable of detecting millimeter-scale ground movement from orbit, they published a finding that reframed what those two sinkholes actually represent. They are not isolated events. They are surface expressions of something much larger happening underground. A vast area of ground between and around the sinks is actively subsiding. Multiple new collapse centers are developing beneath the surface. The area at risk of catastrophic collapse spans several kilometers and includes a state highway, active oil infrastructure, and the subsurface geological record of an ocean that existed 250 million years ago. And the mechanism driving all of it is not something exotic or unprecedented. It is water-dissolving salt. Ancient Permian-era salt, laid down when what is now West Texas was the floor of a shallow inland sea, quietly and relentlessly being dissolved by water finding its way underground through a network of pathways that humanity spent a century unintentionally creating. To understand what is happening beneath the Permian Basin, you need to understand what the basin actually is. Not the economic entity, the oil-producing region, that generates approximately 40% of all U.S. crude production. The geological entity. 250 to 280 million years ago, the Permian Basin was not a desert. It was a shallow, landlocked sea, similar in some ways to the modern Persian Gulf, slowly evaporating in a warm, arid climate. As the water evaporated over millions of years, the minerals dissolved in it precipitated out and settled on the seafloor. Calcium carbonate, gypsum, anhydrite, and in enormous quantities, halite, rock salt. These evaporate deposits accumulated in layers hundreds of meters thick over millions of years, eventually buried under subsequent layers of sediment and rock. The result is what geologists call the Salado Formation, a massive sequence of salt beds that underlies much of the Delaware Basin's subregion of the Permian. In places, this formation is more than 600 meters thick. Salt is not stable in the presence of water. Halite, pure rock salt, dissolves at approximately 360 grams per liter of water at room temperature. That is a dissolution rate dramatically faster than limestone, which forms the basis of the karst cave systems familiar in places like Kentucky or Florida. The same process that creates karst caverns in limestone, water-dissolving rock over time, creates caverns in salt formations, but faster, sometimes much faster. For most of geological history, these deep salt beds were protected from significant water contact by the overlying rock layers and by the natural pressure conditions underground. The regional groundwater system did not have efficient pathways to reach the deepest salt. Then, between roughly 1920 and the present, more than 100,000 oil wells were drilled through the Permian Basin's rock layers. Every one of those wells punched a hole directly through the protective rock layers above the salt formations. Many of those wells, particularly the older ones, drilled in the early and middle 20th century, were abandoned without proper sealing. Their casing corroded, their cement plugs degraded or were never properly installed. What was left was a network of imperfect conduits, some sealed, many not, running from the surface or from shallow aquifers directly down through the protective geology to the salt beds below. Wink Sink 1 formed directly above one of these abandoned wells. The documentation is specific. A well drilled in the 1920s, abandoned improperly, allowed water to access the Salado Formation below. The salt dissolved, a void formed, and in 1980, the surface above it collapsed without warning. This is not speculation about what might happen. It is the documented record of what already did. The 2019 satellite study found something that made the Wink Sink story significantly more alarming. Using interferometric synthetic aperture radar, a technique that uses reflected radar signals from orbiting satellites, to measure surface deformation at millimeter precision, researchers mapped ground movement across approximately 4,000 square kilometers of the Wink area. What they found was not two isolated sinkholes. They found multiple zones of active subsidence. The ground between the two existing sinks is dropping. New depressions are forming underground before any surface expression appears. The entire pattern is consistent with a system of underground dissolution caverns that are growing, merging, and approaching a threshold at which the overlying rock will no longer support itself. They identified two specific areas as being at particularly high risk of sudden, large-scale collapse. Together, these zones cover an area that would make any collapse event dramatically larger than the existing sinkholes. And running through one of these zones is Highway 115, a state road carrying both civilian and oil field traffic. Alongside the road, the pipeline infrastructure that carries crude oil, natural gas, and produced water through this section of the basin. The Permian Basin's economic significance means that infrastructure failure here is not a local West Texas problem. The basin produces 5.7 million barrels of oil per day, approximately 40% of total U.S. crude production. Major pipeline corridors concentrate in this region, connecting Permian production to refineries on the Gulf Coast and to export terminals. A collapse event that severed multiple pipeline corridors would create immediate, significant disruptions to U.S. fuel supply chains and energy markets. But there is a compounding factor beyond the abandoned wells that the full picture requires acknowledging honestly. The oil industry's modern operations have changed the subsurface fluid dynamics of the Permian Basin in ways that extend beyond the legacy problem of old abandoned wells. Hydraulic fracturing, the technique that unlocked the modern Permian shale boom, generates enormous volumes of produced water, the brine that comes up from the formation alongside oil and gas. This water has to go somewhere. The primary disposal method is injection into deep disposal wells, where it is pumped back underground under pressure. The U.S. Geological Survey has established through extensive research that produced water injection is the primary driver of induced seismicity in regions like the Permian Basin and the Oklahoma oil patch. The Permian Basin experienced a magnitude 5.4 earthquake in 2022, the largest recorded in Texas history. Induced seismicity creates new fracture pathways in rock, and new fracture pathways can provide new routes for water migration towards salt formations. The relationship between produced water injection and salt dissolution is less directly established than the connection between abandoned wells and the Wink sinkholes. But the basic physics are straightforward. Injecting large volumes of water into a basin that contains extensive salt formations, changing subsurface pressure gradients, and creating new fracture networks is not a risk-neutral operation. The regulatory framework governing disposal well permits does not systematically evaluate the salt dissolution implications of injection programs across the basin. Texas has an estimated 6,000 to 8,000 documented orphan wells, wells whose operators are legally and financially gone, leaving no entity responsible for plugging. The actual total, including wells from the earliest decades of Permian production that may not be adequately documented in state records, is unknown. Each one is a potential conduit. The state of Texas has a well plugging program that uses industry fees to address orphan wells. The program plugs hundreds of wells per year. The backlog is measured in thousands, and new orphan wells are created faster than the program can address legacy ones. There is one more dimension of what is being lost here that extends beyond infrastructure and economics. The Salado Formation, the 250-million-year-old salt beds that are dissolving beneath Winkler County, are not simply a hazard. They are a geological archive. Salt preserves things. Ancient brine inclusions trapped within salt crystals can contain microorganisms, organic compounds, and chemical signatures from the ancient ocean that deposited the salt. These inclusions are time capsules from a world that existed before the dinosaurs, from the period of the greatest mass extinction in Earth's history, the end Permian event that wiped out approximately 96% of marine species. Scientists studying these inclusions can reconstruct ancient ocean chemistry, ancient atmospheric conditions, and the biological communities that existed in that shallow Permian Sea. As the salt dissolves and the formations collapse, that record is permanently destroyed. Not gradually degraded, destroyed. The void left where salt used to be contains no archive. What does responsible risk management look like for a situation like this? The University of Texas researchers recommended continuous monitoring of the subsidence zones, including installation of ground-based GPS stations to supplement satellite data, and evaluation of the structural integrity of Highway 115 and the pipeline infrastructure in the high-risk areas. They also recommended a systematic evaluation of the abandoned well inventory in the area, prioritizing plugging of wells that penetrate through to the Salado Formation. These are achievable, relatively low-cost interventions that would provide significantly better situational awareness about what is happening underground and reduce the risk of sudden, unannounced collapse events affecting critical infrastructure. What is not achievable is stopping the dissolution process that is already underway. The voids that exist beneath Wink today will not refill. The salt that has dissolved is gone. The question is how large those voids grow before the surface above them fails, and whether the humans and infrastructure above them have adequate warning when that happens. The Wink sinks are not a closed case from 1980 and 2002. They are the visible surface markers of an ongoing underground process. The satellite data shows it is still active. The physics show it cannot simply stop on its own. And the legacy of a century of oil development has left behind the conditions that are driving it forward. The ground beneath West Texas's most productive oil field is hollow in places, and getting more so. That is not a hypothesis. That is what the data shows. And the question of when it matters and how much depends on choices being made now about monitoring, about well plugging, about regulatory frameworks that were designed for a surface industry but govern an underground one. The salt is still dissolving, and the ground above it is still settling, millimeter by millimeter, year by year, until it is not.